Hello Earth Science kids. This video is all about how to read the chart on page 15 of your reference tables in characteristics of stars. So you'll see there are some specific stars placed on this chart. And let's take a look at what the sides of the chart mean. On the left side we have luminosity, and that is how much energy the sun is giving off compared to our sun. So all these different stars, we compare them to our sun. Notice, a luminosity of 1 leads us to our sun. That then is what everything is compared to. So notice the scale is exponential. Every notch is 10 times the previous one. Stars can get incredibly luminous. They also can get remarkably low luminosity compared to our sun. So this side is all about luminosity. On the other side, we also compare small to massive stars, and that works very well for this chart as well. And on the bottom, we have what the surface temperature is. The surface temperature we figure out spectrally, but you can just take a look at a star and see how hot it is. Red stars are not very hot. As the temperature increases, they get considerably bluer, and you can see the colors down here going with the surface temperature: red, orange, yellow, white, blue-white, or blue being the hottest stars. Now when we compare these, and of course luminosity, when we compare, this is not how bright a star appears to us, this is how bright it really is. If we put all the stars the same distance away, that's how they would appear. So when we compare the surface temperature to the luminosity, you would expect that stars that are really hot, these stars, would also be really bright. And you can see that you would be correct. You would also suspect that stars that were really cool would be really dim. And you would also be correct. And you would also then suspect that there's a whole bunch of stars right in the middle that would be getting more luminous the hotter they are. And this whole line that goes right through it like this is called the main sequence. Every main sequence star is early in its life, and really it's not necessarily early in its life, it's living its life, its normal life. What that means is it is burning hydrogen to helium in its core. Every star along the main sequence is doing that. Now stars are mostly made of hydrogen, so the longest period of its life it's spending burning hydrogen to helium. After it's done burning hydrogen to helium, things change. The core collapses right away because there's no more nuclear fires to support it, and because the core collapses, it heats up tremendously adiabatically, simply by the compression of this object. And it gives off so much heat to the outer envelope of the star that the star puffs up and becomes a red giant, or if it's a more massive star, a red supergiant. So the star's outer atmosphere expands tremendously and cools down. Notice the colors become orange-red for the giants. These are red giants or red supergiants. Okay? It will go through multiple phases where it will start the helium burning again and act a little bit more like a normal star, but then it'll soon run out of helium, and it'll go through a number of phases depending on the mass of the star. Eventually, the star will blow off its outer atmosphere, and many of them, most of them, become white dwarf stars. All you're seeing here is the core of a very hot star. The outer atmosphere is gone. So this shows you the evolution of stars. Many supergiants don't go to the white dwarf stage. They go to a neutron star or a black hole stage after they supernova. The brightest explosion you can have gives off the luminosity of 10 billion suns. It's a rather impressive explosion. We have a number of supergiants in our galaxy close enough for us to see with the naked eye, and these are some of them. So why don't we talk about Betelgeuse And if we were to ask ourselves the question, Betelgeuse, how bright is that in comparison to our sun? Well, if we look straight across, draw a line here, you see Betelgeuse is 100,000 times brighter than our sun. What's the temperature on the surface of Betelgeuse? You read straight down, and you see that it's, I'd say, about 3,300 kelvins, right? About 3,000 degrees Celsius. So that's the temperature and the luminosity of Betelgeuse if we were to talk about what color it would appear. When you look at Betelgeuse here, it's orange, red, and that's what Betelgeuse looks like in the sky. You can see it with your naked eye when you look at Orion, that Betelgeuse is that bright orangish star. How about Polaris? Compare Polaris to our sun. Again, you read straight across, and you see it hit here. If that's 1,000 and that's 10,000, I'd say probably about 3,000 to 4,000 times as bright as our sun. And if you look down to get the temperature, Polaris would be just a little bit hotter than our sun. All right, about 6,000 kelvins. You can see just a tiny bit hotter than our sun. What about Alpha Centauri? How hot is that compared to our sun? Look straight down. It's as hot as our sun. Is it brighter? A little bit brighter. It's probably about twice as bright as our sun. So you can use these and take a quick look at any of the stars that they're talking about. Barnard's star is one that we could ask about. How bright is that compared to our sun? And if we look, draw a line over, we see that Barnard's star, this would be a tenth, this would be 100th. So we might be talking about a 500th as bright as our sun, 1/500th as bright. So a very dim star. How does its temperature compare to our sun? Well, while our sun is just a little under 6,000 kelvins, Barnard's star is just a little bit more than 3,000 kelvins. So we can look at any of the stars here and figure out what they're up to. And that's the idea of the characteristics of stars. The one other thing useful to note about this is stars in this end live very long lives. These stars can live hundreds of billions of years. Up at this end, the more massive stars, the much brighter, hotter stars, many of these stars live about 10 million to 100 million years. So these live very, very short lives. These live very, very long lives. That is how you understand this diagram. Our sun is right here. Our sun is slated to live for about a total of something like 10 billion years till it starts going to the red giant phase. And after that, then it only lives for a couple million years. Thanks for watching.